guys, so today we're going to be going over this question one problem from exam one in 2021. Now, this problem is kind of popular, I would say, among the exams, and I believe it was in the homework, so you do have to know how to do this, at least the basics. So the problem tells us that an electric field is given in cylindrical coordinates as this electric field. You may assume that this is a valid electrostatic field, meaning it's path independent. We can choose whatever path we want, and it will result in the same voltage drop. So on that note, it asks us to find the voltage drop between points A and B shown below. So whenever something is in cylindrical coordinates, it might be a little easier to deal with circles, right? So given this, it might be easier instead of, maybe something that might seem obvious, maybe you go straight up and then you go left. Well, this would work if you have rectangular coordinates, because it's very easy. You can say integrate from at x is equal to 2, and then from 0 to 3, right? And then you add it to the integral from y is equal to, or actually, sorry, y is equal to 2, or 3, sorry, from x is equal to 2 to 0. You could do this if you had rectangular coordinates, but you don't have rectangular coordinates. You are given, or not rectangular coordinates, you're given an electric field in the cylindrical coordinate system. So what you should do is try and make circles where you can. In our case, it's easier to see a circle going this. Imagine this is a circle. And this is at what? My goodness, that's terrible. Hold on. That's not much better, but it's going to be good enough. Okay, whatever, imagine it's a circle. So we go from here to here, and what is changing with respect to, distance? Well, so what might be changing? Well, we know rho is going to stay the same with respect to the origin. Rho is the radius of our circle. The radius of our circle is going to be at a constant value of 2, right? So what does this mean? Well, that means our endpoint here we'll call P will be what? 0 to 0 in rectangular coordinates. Now, why are we trying to get stuff in terms of rho, or why are we trying to figure out what is it changing with respect to? Well, this is important because when we're trying to find the voltage drop between 2 points, and our goal is to get the voltage drop between points A and B, this is equal to the integration from A to B of E, the electric field, dotted with the dr differential. Now, in cylindrical coordinates, we know dr. I need to look at my crib sheet here real quick. Dr in cylindrical coordinates is equal to rho hat d rho plus phi hat rho d phi plus z hat dz. In our case, z hat is in the electric field. We have each of the components in there, which is great. When we dot it, we'll figure out which ones we actually need and which ones we don't. That comes later into the problem. Now, we are choosing a path, right? It looks like contour, a line path. We're not going over some surface. We're definitely not going over some volume. Anyways, what we have to notice is that E will depend on phi, the change in phi. So what does that tell us? Well, rho is going to be a fixed value of 2. Phi is going to change with time, so what we're going to do is we're going to label it as phi. Z is going to be stuck at 0 because we're on the xy plane, right? So we're going to let this be 0. This is our E vector, and we're dotting it with dr, which is, of course, we can rewrite this now, or I'll keep it as dr actually. Of course, we're integrating from what points, though? We are integrating on this path from point A to point P. We chose this. Now, what is E where rho is equal to 2, phi is a variable, and z is equal to 0. Well, E will then be equal to 2 rho hat plus phi times 2 over 2, which is 1, plus z hat times 3 times 0, which is again 0 here. And dr, well, what is this? Well, we know dr is going to be exactly what we had up here. So when we take the dot product between them, the dot product between E of, E and dr, this is equal to 2 rho hat dotted with rho hat d rho plus phi hat rho d phi. Well, we know the rho hats, they go away, so we're left with 2d rho. And now for this one, we are left with rho d phi. Yeah, rho d phi, not the hats. We don't need the hats there. And that's E dot dr. Now, the integration from points A to point P, what is that going to be? Well, we have two parts. We have 2d rho, and we have rho d phi. We know rho to be 2, so we'll let this be 2 now. So we have 2d rho. Well, is rho changing? Well, it's not changing. It's going to stay at 2. So 2 to 2. What do we know about an integration when we when we integrate over the same bounds? Well, that's 0. Then we have to add it to the integral of 2d rho from what to what? Well, we're starting at x, which we can assume to be 0, and we're going to the positive y-axis, which can be pi over 2. So this is from 0 to pi over 2, which is then equal to 2 times pi over 2, which is equal to pi. So this is the voltage drop. I'll put this, make sure to put this units, voltage drop from point A to point P. Now we have to worry about the voltage drop from point P to point B. Voltage drop from point P to point B is equal to the integral from point P to point B of, again, E dot dr, and we're going to do the exact same process we just did. From point P to point B, what is changing? Well, we know rho is changing. Rho is changing from 2 to 3. So our E vector will look like this. Rho, it's the variable. Phi is pi over 2, and z is still 0. So what are we going to do? We're going to leave this, and we're going to rewrite our equation in terms of these variables. Rho doesn't change, so we have rho hat, rho plus phi hat, 2 over rho plus z hat, 3 times 0, which again is still 0. Now E dot dr, this is going to be equal to rho, the rho components, they cancel out, or at least the unit vectors cancel out, and we have dr, which is rho hat d rho. So we just have rho d rho. Now for the phi component, the phi's, they go away, but we have a rho d phi, which is 2 over rho times rho d phi. The rho's cancel, perfect. And we don't have a z component because z is 0 in the electric field. So we can rewrite this here. Rho d rho plus 2 d phi is our E dot dr vector. We don't have to worry about phi being pi over 2 because there's no phi's in the electric field, so it doesn't matter. Rho is a variable though. So now what do? The integration from point P to point B for rho d rho. This is going to be from point P to point B, which is rho of point P is equal to 2, the radius of our circle, and rho of point B is equal to 3, which is the distance, again, from the origin. So we're integrating from 2 to 3. Now we add the integral, and now we're doing 2d rho. 2d phi. Does phi change? Phi is going to stay at pi over 2. So again, this becomes 0. We don't worry about it. Now, what is the integral of rho? It's going to be rho squared over 2, evaluated from 2 to 3, which is 3 squared over 2, which is 9 over 2, minus 4 over 2. What is that? That's 5 over 2. So now, when we do the addition of two different voltage drops, voltage drop from A to B is equal to the voltage drop from A to P plus the voltage drop from P to B. So what was this? The voltage drop from A to P we got as pi, and the voltage drop we got from P to B is 2.5. So that is our answer, pi plus 2.5 volts. And hopefully this made sense. I did do a little bit of yapping at the beginning. Hopefully that helped. Otherwise, this is how you do the problem. These are all the steps needed to do this problem. Of course, you can skip steps as you get better at this, but for right now, if you're just starting out, make sure to do all the steps so you really understand the theory. Anyways, hopefully this helped y'all. If you have any questions about this, please let me know, and I'll see you on the next video.